Okay, welcome to lecture here. We're going to pick up with the next topic. And again, these notes should be online if you need them. So since we finished the last one, we'll be moving on to stoichiometry, molarity, concentration. Just a sec here. And as you can see, this sort of handout or lecture is going to cover a number of parts of sections and chapters. I think those are the right sections and stuff. Okay, so in the last sort of chapter we were talking about really reactions, equations, balancing equations, types of reactions. And here in sort of this chapter, we're going to put together a couple different concepts, that concept of balancing equations, and also the concept of grams to moles, moles to grams that we talked about in a previous chapter as well. And sort of put them together to really do stoichiometry. Stoichiometry, again, is really that combination of using an equation to figure out how much, for example, product you may make, how much reactants you started with. So we're going to do really some calculations from chemical equations, and that's basically the stoichiometry part. We'll also get into a little bit about solution, concentration, molarity, and with that, we'll also come back to the idea of titrations, which is also stoichiometry that involves solutions. So again, I think technically in your book it covers a few different sort of chapters and areas from those chapters, but we're going to lead into that here as I keep dropping stuff. All right, there we go. All right, so let's get started here. So really stoichiometry is this idea of using an equation to figure out, what's going on in terms of how much product you may make, how much reactants you started with. And it uses really the relationship that we could get from an equation to help us determine, how much of all that stuff that we would have. So let's just go back maybe to the previous page. So for example, if we had an equation and we had a balanced equation, which when you do stoichiometry, you definitely want to make sure that your equation is balanced. So if we had, say, A plus B goes to AB, and we'll do 2, and we'll do 2, and we'll do 2, for example. And if we have a balanced equation here, from the equation and the coefficients that we have in front, these are what are referred to really as the mole-to-mole relationship. And the mole-to-mole relationship you could get from the actual balanced equation. So in this particular example, actually, let me switch it up a little bit. Let me make this a 4. We'll just pretend it's balanced. All right. So from this a pretend reaction here or equation that's balanced, what we could say is that for every 2 moles of A that we throw in there, we would get out 4 moles of the AB. For every 2 moles of A we throw in there, we could get out 2 moles of B, again, assuming all this is balanced. And we also could say that for every 2 moles of B we throw in there, we could get out 4 moles of AB. So in this particular case, these are all what are referred to as being stoichiometrically equal to each other. Now, equal to each other obviously means that they're not equal in terms of numbers. So in my made up example here, assuming that this is balanced, that the 2 does not equal the 4, obviously. They don't equal each other in terms of numbers usually. But what it does mean is in terms of sort of proportion, what you need to throw in there into that reaction to get it to take place properly, that's sort of the ratio that needs to happen. So it's kind of like when you're baking, right? Or you're cooking, or baking, I guess is good. You know, you need to throw so many eggs in, so much flour in, so much chocolate chips in, right? To get your chocolate chip cookies out. You know, it's sort of the proportion that needs to come out to say bake a dozen cookies or 2 dozen cookies and so forth. And that's really what the coefficients and sort of the mole to mole relationship is here. So again, they're referred to as being stoichiometrically equal to each other, which just basically means it's sort of the right proportion. Now, because they're still technically equalities, you could take any one of these sort of relationships that you get from the balance equation, and you really can write two conversion factors. So for example, for that first one, you can write 2 moles of A over 4 moles of B, or you could flip it if you needed to, 4 moles of, I guess it's AB, of AB over 2 moles of A. And you could do that for any of these sort of relationships. Again, you could write 2 moles of A over 2 moles of B, or 2 moles of B over 2 moles of A. Much like a normal conversion factor that we talked about just with basic sort of dimensional analysis and so forth. You obviously won't use all the conversion factors in a particular equation. You'll just use really the ones that you need. So for example, if you said, hey, I threw in there 6 moles of A, you know, how many moles of AB would I get out? So you could use this, again, like I said, as a conversion factor. You could start with 4 moles of A, or 6 moles of A. We would want to use the relationship to get rid of A, which would be this one, and leave us with AB. And we would get 4 moles of AB on top, 2 moles of A on the bottom. That's going to give you 24 divided by 2 gives you 12 moles of AB. And basically what that number means in this particular reaction is if you started with 6 moles of A, whatever that represents, for example, in grams or whatever it may be, that if everything went perfect, everything went right, you should produce 12 moles of AB if the reaction was perfect and nothing went bad. So really stoichiometry, and people get a little confused about stoichiometry or the whole relationship thing, it's really nothing more than a conversion factor. The difference is instead of say going to a table to get that conversion factor, you go to the actual balanced equation and you use it as a conversion factor. So we use that mole to mole relationship to do that. And again, the mole to mole relationship is nothing more than the balanced equation. So again, always super important when you do these type of problems, or just in general, to make sure that your equation is balanced. So as we talked about when we talked about balancing equations, if you see numbers in it, probably there's a good chance it's balanced. If you don't see any numbers in the equation, you probably should take a moment or so there to double check to make sure that the equation actually is balanced. So we can use stoichiometry to answer all these type of questions that we see on the screen. You know, for example, if we know the mass of what we're starting with, we could do some stoichiometry here to figure out the mass of, say, the products that we make. And you could also go backwards. You could go, if you know how much products that you made, you could do some stoichiometry calculations and work your way backwards to figure out what you started with. And also, you don't even have to actually cross the arrows. So what I mean by that is, for example, if you had your A plus B goes to C plus D, you could do stoichiometry to figure out if you started with A to go this way to C or D, or B to go this way to C or D. You also know, if you know C, you could go backwards to A or B. If you know something about D, you could also go that way. You could also use stoichiometry to do the relationship between two people on the same side of the arrow. So you could do the relationship between, say, the reactants. You know, if you know how much of one reactant you have, you should know how much of the other reactant you should have. You could also do stoichiometry between your products as well. So if you know how much products you produce, one product, and if there's multiple products, you could also use it to figure out how much of the other product you would produce. So sometimes people always think you kind of have to go from reactants to products when you're doing stoichiometry, but you don't. You can see on the left-hand side of the arrow, you can see on the right-hand side of the arrow, you could go from the right to left, left to right, and so forth. Now, basic stoichiometry problems like the first one here we're going to do, basic stoichiometry problems, there really is sort of 4 main steps that you need to do. And these are pretty much the 4 main steps. The first one is, as we've been talking about, you do need a balanced equation. So always a balanced equation. Again, if you're given an equation, you want to make sure that it is balanced by checking the coefficients. If you're given everything in words, just like we talked about with equations, you want to make sure you get the right formulas down. You want to then balance it. This next thing, which is sort of the really important thing, is you want to take whatever they gave you and convert to moles. So in most cases, or in a lot of cases, what they will give you is grams. So a lot of times you'll be given grams and you need to convert to moles. So as we know, to do that, that is the molar mass from the periodic table. Grams and mole, right? Gives you mole. So the molar mass from the periodic table is what you would use, obviously, to convert to moles. Now, they don't always have to be in grams. They may be like, in pounds or some weird sort of unit. I guess pounds not really a weird unit, but some other type of unit. But at some point, you need to take that unit probably to grams and then take those grams to moles using the molar mass. So somewhere along the way, you're going to have to end up at grams and then grams to moles in that conversion. The reason you need to do that is because the third step is really the stoichiometry part. So the third step's when you go to the equation, and again, you basically find the 2 things you're interested in. So the 2 things we're interested in, for example, here would be, say, if we were given A and we're looking to find AB, we would go to the equation, we would find that relationship, and then we would use our 2 conversion factors that are possible and choose the one that works for us, like we did down here in this calculation. We use the one obviously on the right, and that will allow you to go from what they gave you to what you're actually interested in. And that's really the basis of stoichiometry. In stoichiometry, you sort of have information about something you're not really interested in, but you need to use that information to get to what you are interested in. And that's really where that mole to mole relationship. But ultimately, because stoichiometry is a mole to mole relationship, you need to do step number 2 and make sure that you're in moles before you get to step number 3. Lastly, once you're done with step number 3, you will always be in moles if you did it right. So at that point, they may want moles as the answer. Then you can put a box on it. They may want it in some other unit like grams. So then you might have to use the molar mass at the end. They may want something like pounds where you may have to do 2 or more conversions. But usually at the back end, just kind of like number 2, a lot of times you are at moles, and usually you'll need to use the molar mass going the other way to get to grams. Again, not always going to be grams at the end, but that's a very common sort of thing. So no matter how crazy the reaction may look, how crazy the equation may look, or the numbers that you got, really, if you just follow these 4 steps sort of in these order, you usually will be pretty good on any stoichiometry problem that you need to do. So let's take a look at one and give you a chance here. So why don't you give this a go, I think. So why don't you figure this out? If 209 grams of methanol, which is this guy here, are used up in a combustion, what is the mass of water, which is over here, this produced? So why don't you take a few moments, see how far you get. I'll give you some numbers that you might need from the periodic table. Carbon is 12.01. Oxygen is 16. And hydrogen is 1.008. That's all I need. All right, take a few minutes, see how far you get. Again, try to follow the 4 steps there and see what you come up with. And obviously, we'll talk about it here in a minute or so. Okay, let's take a look here and see how we're doing. So again, this is basically a stoichiometry problem. So we want to just follow those steps. Again, a basic stoichiometry problem. So first step is a balanced equation, which would be here. Again, I do see coefficients, so I'm assuming it's balanced. We can just kind of quickly look. We got 2 carbons on each side. We got 7 hydrogens, 6 and 6 is 12. So it's 8 and 4 is 12 oxygens there. And we have 8 hydrogens as well, 6 and 2. So everything's balanced. The next thing that we want to do is take whatever they gave us and convert it into moles. In this case, we do need to do that as we're given 209 grams of this guy here. So since we have grams and we want to convert to moles, we do need the molar mass of CH3OH, again, from the periodic table, 12.01 for our carbon, plus we have 4 hydrogens at 1.008 each, plus we have 1 oxygen at 16 from the periodic table. And if we do all that, that is 34, I think, 3204 grams per mole. So we're going to use that again to go from grams to moles. So the second step is take the grams that they gave us, which is 209 grams of CH3OH. We're going to use the molar mass from the periodic table, which is our 3204 grams per mole, grams on the bottom so that it cancels out. And if you got an answer at this point, and you don't necessarily have to get an answer at this point, but if you did, looks like you got something like 6.52310 moles of CH3OH. Any questions on that so far? The only thing we really have done up to this point is convert our grams into moles, but we're not really interested again in the methanol here. We're interested in the water. So this is where step number 3 comes into play. We need to find the mole to mole relationship. So we can see from the equation, that's what we were given. This again is what we're looking for. So we can see that it is for every 2 moles of CH3OH, you get out 4 moles of H2O. Again, we're going to use that as a conversion factor. So we want to get rid of moles of the CH3OH. So we take our 6.52310 moles of methanol. We're going to use that relationship so that the moles of methanol cancel, which means 2 moles of methanol, 4 moles of H2O. That is the stoichiometry part. That is the part that's going to convert us from what we're not looking for to what we are interested in. And it looks like you end up with something like 13.042 moles of water. And again, that is the stoichiometry part that allows us to convert. We're close to what we want, but we want the mass. So usually the mass is something like grams. So we do want to do step number 4, where we're going to take our moles and we're going to convert it into grams, which means we need to go back to the periodic table and get the molar mass, in this case of water, because we've converted to water. And that means that we have 1.008 times 2 plus 16 gives us something like 18.02 grams per mole. 1802 is going to actually go on top here so that the moles will cancel. And if you do all that, 235 grams of water would be produced. So you can see the same 4 steps, although I did break it up step, and I did break it up into step and got an answer after each step. You don't necessarily have to get an answer after each step. You could do just one long calculation if you want, where you don't get an answer. If you do get answers in between, like I sort of did here, I would again recommend that you take each answer to a good number of digits and kind of round it up at the end when you're all said and done. So in terms of the only numbers that we had was 209, which is like 3 sig figs, which is why we rounded over here to about 3 sig figs when it was all said and done. But in between, if you do get an answer, you probably want to wait and sort of round to the end. Any questions on those steps? So this is really a basic stoichiometry problem. You just want to follow those steps in order until you get what you're looking for in terms of the answer. What this number really means is if I put in 209 grams of methanol into this reaction, everything went perfectly fine. Everything went according to plan. There was no side reactions. You didn't drop anything. You weren't a klutz when you did this. This is, in theory, how much product we should get. This is also sometimes referred to as the theoretical yield. And the theoretical yield is the amount of product that you should produce based on the reaction or the equation and how much you started with. If, again, everything went perfect, nothing bad happened along the way. Any questions on those steps there? Why don't you try one more here? Let's get it, has it there. And let's go. Let's do it here. Let's say you had this reaction here. So how many grams of H2 did you start with if you produced 125 grams of NH3? So why don't you give that a go and give you some info. Nitrogen is 1401 from the periodic table. Hydrogen is 1.008 grams per mole. So in this one, we want to know how many grams of H2 we would start with if we made 125 grams of NH3. Give that a go. I will as well because, I just made that up. So we'll see how we come out. Clear some room here. Okay, so let's see how we're doing. So same idea here. We have a basic stoichiometry problem. So first things first, we want to make sure our equation is balanced, which I hope it is, unless I messed up there. So we got 2 nitrogens, 6 hydrogens, so we're all good. We also see that the only number that they gave us in this case is 125 grams of NH3. So we do need to do the conversion into moles. So in this case, we have NH3. So again, from the periodic table there, a nitrogen is 1401 plus 3 times our hydrogen, going to give us a molar mass for NH3 of 1703 grams per mole for our NH3. So that's the second step we would do. We're going to take the 125 grams of NH3. We're going to convert it into moles using the molar mass from the periodic table, 1703 grams per mole. Grams will cancel, and if we take 125 divided by, that gives us 7.338, we'll call it. Problem though, we are still in NH3, but we're interested in this case in terms of H2. So this is where the stoichiometry comes into play. From the actual equation, we can see that for every 3 moles of H2 we throw in there, we do need to get out 2 moles of NH3. So we're going to use that as a conversion factor. Here we want to get rid of the NH3, so the NH3 is going to go on the bottom, just like a normal conversion. Opposites cancel. Up on top will be our 3 moles of H2. And if we do that, looks like 11.01 moles of H2. Now that number would represent the theoretical yield in moles, but actually it wouldn't be the yield because we're going to our reactants, but that would be our answer in moles, but we're interested in grams. So we do need to do sort of our fourth step, which is take the moles of H2 and convert it into grams. So again, we would need to go back to the periodic table and take 2 times 1.008 to get our molar mass there of H2, 2.016. So the last step we would do is take our 11.01 moles of H2. We're going to times it by the molar mass of H2 as I run out of room on this page. And if we do that, we will end up with about 22.2 grams of H2 we started with. So same 4 steps, step 1, step 2, this was step 3, the big stoichiometry move, and this would be step number 4, convert it into grams. Any question on any of those steps? So you can see that you can go, obviously, from left to right, right to left. As I said, you can stay in one side of the arrow or the other. Any questions on sort of basic stoichiometry problems? It really is just sort of those 4 steps sort of in order. If something is done for you, also sometimes people do weird things. So for example, in the second step over here, if you started with a number that's in moles, you don't have to obviously unconvert it just to reconvert it. So sometimes people do weird things like that. So obviously if one of those steps is sort of done for you, you just move on to the next step along the way. Any questions on basic steps here for stoichiometry? Okay, so what we're going to talk about next then is a little bit different sort of stoichiometry problems. And these are ones that are referred to as limiting reagent type problems. And limiting reagent type problems are problems that occur in stoichiometry where basically in reality, when you do a reaction, there's usually a reactant that gets used up first. And that is what's known as the limiting reagent or the limiting reactant. So the limiting reagent is the one that is the reactant that gets used up first. And there's one that you have plenty of, which is the excess reagent. And it's actually still there at the end of the reaction. So it's kind of like when you do a reaction, you are going to run out of something first, basically. And whatever you run out of first is your limiting reagent. Whatever you got plenty of is your excess reagent. It's kind of like if you ever bought hot dogs and hot dog buns. I forget which one is which, but I think they used to sell hot dogs in packs of 10 and the buns were like packs of 8. And you always ran out of buns before you did hot dogs. And again, in that case, the buns would be limiting reagent. The hot dogs would be the excess reagent. You could also figure out how much excess reagents left over as well at the end of the reaction. So if we look over here, our kind of double red circles are O2, our blue and red circle is our NO. And then our guys that have 3 circles is our product. So we can see that as we go through here, we have some O2s still left over, just like they were at the beginning of the reaction. And that would imply that those guys are our excess reagent, while we have none of the NO guys, the blue and red circles 2 together at the end of the reaction. And that would imply that the NO is our limiting reagent. Like I mentioned before, the excess reagent, you could also figure out how much is left over. So in this case, we have 3 molecules of O2 left over, none of the NO that is left over as it's limiting. So why is that important? Well, it's important because, for example, if you did this, as we see here, this is our limiting reagent, and this is our excess reagent. In order to make our product here, we need both of these guys, right? So in order to actually make the product correctly, both of these guys are needed. So as soon as this guy runs out, there's going to be no more product being made. And that's why limiting reagents are important, because it is actually the limiting reagent that determines how much product you can make, because as soon as it runs out, there's no possibility you can make any more product. So it is always the limiting reagent here that's the important one, because it basically determines how much product you'll make. So how do you know if it's a limiting reagent problem versus, say, a basic stoichiometry problem like we've been doing? Well, one big key is what information is given to you. So for example, if you look back at the 2 little examples there that we did just previously, in each of those examples, we were only given information about one thing. So one thing in the equation is all that we were given. And when you're only given information about one thing in an equation, it is really just a basic stoichiometry problem. The way you can recognize sort of a limiting reagent problem is you will typically be given enough information about all of the reactants to get to moles. So typically that's 2 usually. So if you're given info about both reactants, it doesn't always have to be 2, but usually it is, then you know it's a limiting reagent problem. And when I talk about information about the both reactants, technically speaking, you have enough information to get to moles. So whatever they give you about each of those reactants, you have some type of way that you could do a calculation to get yourself the moles of each of those guys. And that definitely is how you know it is a limiting reagent type problem. So what does that mean? There's actually multiple ways that you can solve a limiting reagent type problem. I'm going to show you a way that maybe you haven't done before, and it's kind of a good way to do it because it does help you kind of quickly answer a lot of questions that you're typically asked. I'll show you sort of maybe another way as well, which is more of a traditional type way that maybe you've seen before. But like I said, to be truthfully honest with you, there's maybe 3 or 4 different ways you could kind of approach limiting reagent problems. So if you have learned a way previous to this class and you like doing your limiting reagent problems that way, you're more than welcome to do it, as long as it's obviously a legitimate way of doing it. You didn't make it up yourself, I suppose. But if you like the way I'm going to show you, you could use that. The way I'm going to show you is something that if you continue on to 200B, it's a calculation that you will do a lot in 200B, a very similar type calculation. So it will sort of benefit you, I think, maybe as well if you continue on to 200B, because you'll see a very, very similar type calculation when you get there. But again, if you've sort of have a way in your head that you usually do them, should be fine. Honestly, no matter which way you choose, everybody should come out the same in terms of the answer. So what we're going to do then is, let me think how we'll do it. Okay. All right, we'll start with this problem. I'm going to show you sort of maybe the newish way of doing it, and then we'll look at a different way. So let's take this problem, for example, here. In one process, 124 grams of aluminum is reacted with 601 grams of iron 3 oxide. We want to know how much aluminum oxide is produced. Okay. So the first thing that when you see this problem is you should know it's a limiting reagent problem because I have grams of aluminum, which is a reactant. I also have grams of my iron 3 oxide, which is also a reactant. So because I have grams of both of those, I am able to get to moles of both of those, which is automatically sort of the light bulb that should pop off and go, oh, this is a limiting reagent problem, which means somewhere along the way, you need to figure out which one's the limiting reagent, because that is typically the one that will determine how much product you will produce. So the first steps, 2 steps are really the same no matter sort of what approach you take in any sort of way. The first thing is obviously we want to balance the equation, which it is balanced. The next thing that we want to do is take whatever they gave us basically and convert it into moles. So the first thing we would want to do is take 124 grams of aluminum. We would want to go to the periodic table for aluminum, and that's 2698, and convert that into moles. So that's going to give me we'll call it 4.596 moles of aluminum. We would also want to do the same thing for our iron 3 oxide. Again, going to the periodic table, we have 2 irons at 55.85 each, plus 3 oxygens at 16 each, gives us 159.7 grams per mole. And again, that comes from the periodic table. So 601 divided by 159.7 gives us 3.763 moles of our iron 3 oxide. All right, so the opening part here is pretty standard no matter sort of what way you do it. So what I'm going to show you now is a way you could do it, which is sometimes referred to as an ICE table. And ICE means initial, change, and for us, it will mean end. For if you go to 200B, it will mean equilibrium. So you'll use equilibrium there. So it'll be slightly different, but kind of the same concept. So what we do is we take our equation and we do our ice table. So initially what we're going to put is our starting moles of each of them. So we had for aluminum 4.596 moles. For our iron 3 oxide, we have 3.763 moles. And initially, we could assume that we have 0 of our products. We haven't made any products yet, so we'll assume that is 0. So that takes care of the initial part, not too bad. The change part is usually represented in an ice table by a letter, and it's usually X. And X represents the change. So if we assume this reaction is happening, it is going to be proceeding from reactants to products. So we assume that this reaction is heading in that direction, which means as this reaction takes place, the amount of reactants should decrease with time, right? Because we got to use our reactants to make our products. So we're going to decrease the reactants. And with time, we should increase the amount of products that are being made. And that's represented by minuses and pluses. So on the reactant side, it would be minuses. On the product side, it would be pluses in terms of X. The other really important thing is the stoichiometry part of it. And that stoichiometry comes from the coefficients, right? So when I do the change part in an ice table, this would be minus 2x. The 2 takes care of the mole to mole relationship and the stoichiometry of it, minus x, because the coefficient here is 1. On the product side, it would be plus x, coefficient is 1, and plus 2x, coefficient is 2. So really important when you do an ice table and you get to the change part, you actually do need to take the coefficients into account, because when you do so, you're basically doing the correct mole to mole relationship. If you don't do that, then your answer is going to be wrong, because it's basically the same step as when we did the mole to mole sort of conversion. That's what those coefficients will do for you. That means when we get to the end here, we will have 4.596 minus 2x, 3.763 minus x, x, and 2x. First off, any questions on sort of the ice table, the setup here? Okay. So because it is a limiting reagent problem, we do need to figure out which one is the limiting reagent. So the way that we figure that out is we take both of our reactants and we set them equal to 0. So if we do that for this guy here, this would give us 4.596 minus 2x equals 0. This would give us that x is equal to basically divided by 2. So we're going to take 4.596 divided by 2 gives us 2.298 moles is what that is. We will set this guy equal to 0. 3.763 minus x equals 0. That's pretty easy to figure out. X is equal to 3.763 moles. At this point, to determine which one is your limiting reagent, you want to find the one that is the smaller number. So this number here is larger than this number, which means this number here is not the right one. This would be the correct one here, as it's the smaller. So that x value would be the correct x value to use here. And why is that important? Because that x value, if you go back to your table, is this x value, it's this x value, it's this x value, and it's this x value. It's every x value in that table, which means for the question, we wanted to know how much grams of aluminum oxide. So we see from the ice table here that aluminum oxide is equal to X, which means the moles of aluminum oxide equals X, which means we already know what X equals, that we have 2.298 moles of aluminum oxide, which we then can convert into grams by taking the moles and the molar mass of aluminum oxide from the periodic table And aluminum oxide there is 2 times 2698 plus 3 times 16 is 100 and, we'll call it 102, I guess. It's pretty close to what it should be, I think. So that's 102 grams per mole. And that would get us 234 grams of aluminum oxide. And again, this would be a product. So this would be our theoretical yield here. Now, why this method is kind of a pretty good method is, in addition to being able to find aluminum oxide really quick, if we also wanted to know how much iron that we actually made, we could also find that out very quickly as well by going to our ice table, and within pretty quick period of time, we know that iron is equal to 2x, so we could take 2 times our x value, and we would see that we produced 4.596 moles. And you could times that by 5585, which is the molar mass of iron. And you would see you produce 257 grams of iron very quickly, which wasn't asked in here, but you can see really quickly you could figure that one out. You also could figure out a very common question that's asked in these type of problems, which is how much of your excess reagent would be left over. So since we determined that the limiting reagent was the aluminum, that by default means that this guy here would be our excess reagent. And from the table, we could see that the excess reagent would be 3.763 minus x, which is 2.298. And that would tell us really quickly that we had 1.465 moles of our excess reagent left over, which we then could times by the molar mass, which we have of that, which is 159.7 grams. And we would see we had about 234 grams of our excess reagent left over. We started with 601 grams of it. We have 234 grams of it left over. So by doing sort of the ice table here, you can really quickly answer pretty much every question that could ever be asked of you in terms of a limiting reagent problem relatively quickly, without necessarily having to go back to sort of step one and do sort of separate calculations and kind of start at the beginning. So it's a nice way that, you could answer usually how much product you'll make. You could also answer, how much excess reagents left over, which is a very common way as well. Any questions on that approach? All right, so I think here I have this one. I do, I think. Yeah. So here's another approach in terms of how to do these problems, and this might be more like what you have seen before. So one approach is to do this calculation here. So one approach is to do a stoichiometry calculation where you take one of your reactants, which in this case is the aluminum, and you want to figure out how much of the other reactant you would need to completely use it up. So in this particular case, that is what they did here. They took the grams of aluminum, they converted aluminum into moles using the molar mass. They did the mole-to-mole relationship between the reactants, which is a 2-to-1 relationship, and then they converted it into grams. And basically what this number is how many grams of iron 3 oxide is needed to use up all of this. And what they found was that in this calculation, they needed 367 grams of iron 3 oxide to use it up. And what they see is they started with 601 grams of iron 3 oxide, which, just like what we determined, that would tell you you have enough of it. And that tells you, just like we did, that this is our excess reagent. And by default, this would be your limiting reagent. So then what they did is they will start always with the limiting reagent. So they will then go back and do a calculation between aluminum now, like we did, and our aluminum oxide here to figure out how much product you would make. So this is a very common approach where you basically compare the two reactants and see how much you need of one to use up the other and see if you have enough. And then at that point, they did a calculation here with the limiting reagent. So again, they're converting our grams into moles of the limiting reagent. They're now doing the mole to mole relationship between the limiting reagent and the product they're looking for, which is a 2-to-1 relationship. And then using the molar mass like we did, they will end up, as you can see, 234 grams, exactly like what we got in terms of our answer as well. The difference with sort of this approach is if you then want to figure out how much iron, you need to then go do another calculation. If you want to go back and figure out how much of your excess reagents so left over, you need to go back and do some other calculations. So again, the ICE table sort of does it for you very organized, and you can very sort of quickly, within one or two kind of quick calculations, figure out everything that you would need. But this is a very common approach. Kind of the third common way that people do limiting reagent problems is essentially they will do, actually we could look at this, they will do basically two calculations like this. Well, they'll take one of the reagents and go all the way to the product they're looking for. And then they would do the same calculation starting with this guy and figure out how much product it would produce. And whichever one produces the smaller amount, that would be both your theoretical yield and your limiting reagent. So that's like your third common way to do these problems, is just to do two separate stoichiometry problems, one from each reactant to the product, and whichever one produces the smaller amount would be both your limiting reagent, whatever one that was, and whatever you produce would be your theoretical yield. This again would be our theoretical yield here, as it is from the equation how much product we really should make. Any questions on any of those approaches? Again, like I said, if you're more comfortable doing it one of those other ways, you're more than welcome to do so. You don't necessarily have to do the ICE table, but A, it's a calculation that you'll do a lot in 200B, and it might help you to get some practice doing it. And B, it does a lot of times get you a lot of the answers very quickly without maybe having to start back from the beginning and going to through all those calculations. Any questions on any of that there? All right, so let's talk a little bit about yield, since we're talking about the theoretical yield here. There is sort of three yields that we deal with. One is the theoretical yield, which is essentially what we just calculated there. The theoretical yield is really your maximum yield. It is basically the amount of product that you should produce based on the reaction or the equation and how much you started with. So for example, in that last one, the 234 grams was the theoretical yield. Again, what that means is if everything went perfect, there was no side reactions, like I said, you didn't like lose anything along the way, that is in theory how much product you should produce. Now the actual yield is pretty much what the name implies. It is actually how much you produced when you did this reaction. So typically speaking, the actual yield is less than the theoretical yield. And if it's more, then probably something didn't go so well for you. How we use both of those yields is we typically, for a reaction, will calculate what is known as the percent yield. The percent yield, you take the actual yield divided by the theoretical yield. That could be grams divided by grams, moles divided by moles, really any units as long as they're the same. But the actual divided by the theoretical times 100%. And typically around 100% is perfect. Most people aren't perfect, so high 90s is usually really good. If you go over 100%, which is possible in real life situation, you could get a percent yield higher than 100%. The bad news for that is it usually doesn't mean a good thing. It usually means somewhere along the way you screwed up. So very, very common place where that happens is, for example, if you did like a precipitation reaction and you made a precipitate on some filter paper, and this filter paper is probably going to be pretty wet, for example, just from the process of filtering it. And if you don't wait long enough for it to completely dry, when you reweigh it, you're going to get all that extra water weight as your product, which is really is not. It's just the paper that's wet. And you'll get actually a higher actual yield than your theoretical yield. And that's usually, again, a bad indication. So not to be confused, percent yield is not the same as percent error. Percent error is like how good you did, right? You want a low percent error. Percent yield is also kind of how good you did, but you want actually closer to 100%. So if you got like a 2% yield, that was a terrible experiment, yes. So if you got like close to 99% yield or 98% yield, pretty good in terms of that experiment. All right. Now, again, the actual yield in most problems are given to you. So this is usually given in a problem. The theoretical yield you need to calculate. So the theoretical yield could be just a basic stoichiometry problem to calculate it. It could also be a limiting reagent problem to calculate it, but usually the theoretical yield you do need to calculate. Any questions on that? So why don't you try one here and see what you come up with. Let's see here. All right, why don't you try this one here and see what you come up with. So if you take 2.46 times 10 to the 7 grams of TiCl4 molar mass from the periodic table, 189.7 grams per mole. And magnesium, which is 24.31 grams per mole. Calculate the theoretical yields of Ti and also the percent yield if you had 5.42 times 10 to the 6 grams of Ti. So see what you come up with, and we'll talk about it. I'll give you one more piece of information, which is, I think, Ti. You'll need. Ti is 4788 on the periodic table. All right, take a few minutes, see what you come up with. We're looking for the theoretical yield and also the percent yield. Think about what type of problem it is. Should hopefully have an idea. Okay, so let's see how we're doing here. So even if you haven't finished, hopefully you're on the right track. So a couple things here. We have the grams of TiCl4, and we have the grams of magnesium. So automatically what we see is we do have the grams of each of these guys here, which means we are able to get to the moles of each of those. And again, that should mean that this is really a limiting reagent problem. And again, that's keyly how you can determine that is if you're given the starting amounts of both guys and you're able to get the moles. So we do need to figure out that limiting reagent, which means, again, you can do it one of those three ways. I'm going to continue with the ice table just to kind of show you how to do it that way. But again, if you choose one of the other ways that maybe you learned before that we just talked about, again, we all should end up pretty much with the same answer when it's all said and done. Now, we want to make sure we have a balanced equation, which we do. The next thing we do want to do really is convert everybody into moles. They were nice enough to give us the molar mass. If they didn't, we would need to go obviously to the periodic table to do that. So to get the moles of the TiCl4, we would take our 2.46 times 10 to the 7 grams. Again, use the molar mass that they gave us, and we would get from the periodic table if they didn't give it to us. And that gives us 1.3 times 10 to the 5 moles. Again, you want to make sure you do use your exponent button. We'll also want to do the same thing for our other guy, which is magnesium. And 1.13 times 10 to the 7 grams. Again, they gave us the molar mass, but if they didn't, we would go to the periodic table to get that. And 4.65 times 10 to the 5th moles of magnesium. So really, this is our starting amount, right, of each of these guys, just converted into moles. Any questions on that so far there? Okay. So again, like I said, I'm going to do it the ice table approach to sort of figure it out. Again, you could do it the other way, but again, so you can see it. So find the right page. I'm going to start with the equation here. So I have TiCl4 plus a couple of those gives me Ti plus 2 magnesium chlorides, right? Now, we're going to initially start with what we just calculated there on the previous page. We're going to start with the moles of the TiCl4, which is 1.3 times 10 to the 5th. And again, those are moles. And magnesium, we had 4.65 times 10 to the 5th moles. Like normal, we could assume that we have not made any products yet, so those guys would be 0. The change part, again, needs to take into account the coefficients, so you have the right mole-to-mole relationship. So coefficient here in front of the TiCl4 is 1. We're going to do minus x because it should be decreasing. We should be using those reactants to make products. Coefficient here in front of the magnesium is 2, so this would be minus 2x. Again, that 2 takes care of the mole-to-mole relationship. Product side, we're going to be gaining. So this would be plus x, coefficient here is 1, and plus 2x. That means that when we get to the end, we have 1.3 times 10 to the 5th minus x, 4.65 times 10 to the 5th minus 2x, x, and 2x. Any question on how the ice table came about, where any numbers came from, or anything like that? So remember, at this point, we want to still figure out which one is the limiting reagent. And to do that, we're going to set, like we did before, each of these guys on the reactant side equal to 0. So we're going to set this guy equal to 0. We're going to set this one equal to 0. And we're going to solve for x. So if we do this, this x is pretty easy to find out. It is 1.3 times 10 to the 5th. If I do this x, essentially we're going to divide that number by 2. So that would be 4.65 to the 5th divided gives us, try writing with the right side there. There we go. 2.33 times 10 to the fifth. Again, here, the one that will be the limiting reagent is the smaller number. So this is too big. And because this is a smaller number, this tells us that the TiCl4 is the limiting reagent, and the magnesium by default would be your excess reagent. Any questions on that there? So at this point, we can now solve for a bunch of stuff that we're looking for. Mainly we were looking for Ti. So we know that the moles of Ti from the table is equal to X, which means we have 1.3 times 10 to the fifth moles of Ti, which we then can convert into grams by using the molar mass from the periodic table, 4788 grams per mole of Ti. And that will get us 6.22 to the sixth grams of Ti. This number here would be our theoretical yield. Any questions on that? Again, if it wasn't asked for in this particular case, but if we wanted to, and again, sort of the benefit of this sort of approach is if we wanted to know about magnesium chloride, for example, we then could figure out really quickly the moles of MgCl2, which would be 2 times X. So that would be 2 times 1.3 times 10 to the fifth. And if we did that, 2 times 1.3 to the fifth gets us 2.6 times 10 to the fifth moles of MgCl2. And if we use the molar mass of that, which is like 95, 21 grams per mole, we would end up with something like 2.48 times 10 to the 7 grams of MgCl2 was produced. And again, you can see pretty quickly we could get to our second product, which wasn't asked for. And again, most often though, this question is asked how much of your excess reagent would be left over. And again, using the table, you can answer that question relatively quickly by coming here and going the moles of magnesium that's left over. Would be 4.65 times 10 to the fifth minus 2 times X, which is 1.3 times 10 to the fifth moles. And we would see that we had something like 2.1 times 10 to the fifth moles of magnesium left over. And again, if we multiply that by the molar mass of magnesium, which we have, we would have something like 4.98 times 10 to the 6 grams of magnesium left over. So again, sort of the benefit of this, like I said, you could very quickly get sort of to the other questions that are asked of you and kind of find those answers relatively quickly. Any questions on that there? Now, we obviously still have one more piece of information to calculate for the actual problem. So we now have our theoretical yield. And remember that what we're looking for is also the percent yield, which is our actual divided by our theoretical times 100%. So the actual actually comes from the problem. So this is our actual yield here. And the theoretical obviously is what we just calculated. So to finish up this problem with what it was actually asking for, which was the percent yield as well, we would take our percent yield is our actual divided by our theoretical times 100%. That means our actual, which was given to us in the problem, 5.42 times 10 to the 6th grams, divided by the theoretical that we just calculated, times 100%, gives us a percent yield of 87.14. Not terrible, not super great, but not horrible, I guess. Any questions on the percent yield calculation? So usually in a textbook problem, the actual yield is given to you. Only usually in a laboratory experiment, which you have to sort of figure out the actual yield. You actually did this, I think, in one of those experiments. I think I can't remember which one. I think it was the chemical formula one. I think the percent yield, sort of. Any questions on that? All right. So again, like I said, if you hopefully did it the other way, or if you're more comfortable with it as well, again, you should have ended up with pretty much the same answer. Any questions on any of that stuff? All right. So it's a good place to stop here. We'll continue lecturing on this obviously tomorrow. In lab, like I said before yesterday, we're just going to push everything back a day. So today we will focus on the study assignment E or F. I think it's F maybe. So it should be the redox study assignment. We're going to talk about, at the beginning next time we'll show you the next way. We're just kind of over time here. So we'll start and we'll look at the other way at the beginning tomorrow. So we're doing a study assignment, which I think is F, which I think is the redox ones. So we will talk about how to balance those type of ones like you find in your study assignment during lab today. And then I think we'll move the experiment for today, which is the redox reaction experiment video, until tomorrow and stuff like that. So if you just look at the sort of lab schedule, just move everything back a day and it'll be okay. We're going to cut out one of the titration days. We have way too many to begin with anyway, so everything will work out okay. All right, so about, just run a little bit over, we'll start lab about 9:50. And again, we'll have a little lecture on how to properly balance those redox reactions, and then you can work on the study assignment. All right, I'll see everybody in about 20 minutes or so. Make sure you type here if you haven't done so already.